So, in today's outing, I'm going to talk about a little bit more about the conservation of linear momentum. And to recall, in the conservation of linear momentum system, where the total momentum of the system at any instant of time, before an event takes place or after an event takes place, whatever, at any moment of time, the net sum of the momenta is a constant, and therefore it is conserved, and therefore it is invariant for a given case that we have. And this happens in the system that we consider as an isolated system. When I say isolated system, I'll say that no external force is acting on whatever are the contents, whatever the activities are happening in this system. Activities in the system may occur. The masses which are contained in this isolated system may change their velocities. They may be accelerated, and we can define the velocity and acceleration as a function of time. But because no external force is acting on the isolated system, only internal forces, they act. And the net sum of all these forces, sigma 1 to n, which means F1 plus F2 plus F3 plus and so on, plus Fn, if there are n particles associated with it, then this will be equal to 0. And remember, I told you that what Newton did not write in Principia Mathematica, what Newton proposed to, but he died before another publication for the Principia could take place in his lifetime. Then what he said was, I repeat again, for F1 or F2, for F3, for Fn, that describes at a time the state of the body. And he stated that the state of a body is determined by the forces acting on the body and not by the forces which this body exerts on other bodies. Okay? I repeat again, the state of any of these bodies contained in the system is determined by the forces, okay, which are exerted on this body by other bodies, and not by the forces that the body exerts on other bodies. So this is clear. To determine the state of a body, to define these forces, this must be made clear. In the today's outing, we'll just take a couple of examples from the conservation of linear momentum. Many other examples are there, but for us it will suffice, and then you can go back to your books and look for other examples. So the two examples that I'm going to take today, one is the case of a gun. Okay, the one is the case of a gun, and then there is a shot which is fired from the gun. Okay, and then we'll try to know if the shot leaves the gun with the velocity, say, okay, I'll come to that, with a certain velocity, then what happens is that if I take these two bodies. One I call the gun and other I call a shot. Okay. Now the gun is shot at a time t is equal to 0, which is also a very funny thing. T is equal to 0. We don't know when time t is equal to 0 is started, but this is what we do in physics, and with time we understand what is this. This is the beginning of the event. So there are, this time t is equal to 0 has got two aspects. One is t is equal to 0 minus, and the other is t is equal to 0 plus. Okay, and both are equal to 0. The event takes place, the system releases the shot, and then the shot is released at a time t is equal to 0 minus, and the shot is released at a time t is equal to 0 plus. So 0 minus and 0 plus, both of them occur at 0. This has to be understood very clearly by us. Okay. So let the gun be there, and this is the gun and this is the shot. I don't like to make the shape of the gun because guns appear to me to be vulgar. Although most of the mechanics this developed in those days when they believed too much on the gun. They created guns and they killed each other, and Newton was also working with the armory division of the British where the gun was a very important thing. Anyway, so the gun is there and there is a mechanism by which the shot leaves the gun. I don't care about that also. Then what happens is that the shot travels with the velocity in the forward direction. And at this time, t is equal to 0 plus, this event happens and the gun recoils. The gun recoils with another velocity, which may be, because the gun is heavier than the shot, the gun is heavier than the bullet, or the cannon is heavier than the shot. So anyway, there is a recoil velocity. And there is one more point to it, that at the time of release of the shot, there is a force. But thereafter, there is no force. The force stops. The event takes place. And the gun and the shot, they travel like this. So if I take the mass of the gun equal to mass of the gun, mass of gun, taken as m1, and mass of the shot, mass of the shot, this is taken as m2. So at time t is equal to 0 minus, this time actually the gun was having a mass m1 plus m2, and suddenly as the event took place, the mass of the gun becomes equal to m1, and the mass of the bullet, this becomes equal to m2. Okay. Now let us take the velocity of the gun velocity of the gun, velocity of gun, velocity of gun after the shot, after shooting, after the event has taken place. After shooting, let me call it capital V meters per second. Say, capital V meters per second. And the velocity of the shot, velocity of shot or bullet, as it leaves the nozzle of the gun, yani after shooting, let it be equal to small v meter per second. So let us analyze this. At t is equal to at this moment the total momentum of the system, because the gun is at rest, the bullet is at rest, the shot is at rest, and the total momentum of the system at t is equal to 0 minus, at t is equal to 0 minus, the gun is at rest and the bullet is at rest. So we can say T is equal to 0. The momentum of the system at that instant of time is equal to 0. And the momentum of the system P at T is equal to 0 plus and thereafter T is equal to 0 plus and thereafter, assuming that there is no air resistance thereafter. Okay. But at least at this time t is equal to 0 plus. This is equal to, I can write now as separate masses, m1 that of the gun multiplied by the velocity of shooting v. So m1v plus m2 small v. And then we apply the simple law of conservation of momentum. The law of conservation of momentum says that the momentum, when there is no force applied externally on the system, when the force applied externally on the system is equal to 0, then this total momentum, for example in this case there are only two bodies, m1 the gun with the velocity v and m2 the bullet with the velocity small v. Okay, and this will be equal to the same momentum that existed from before, and that momentum is equal to 0. So all we have to apply in our analysis is that this is equal to 0. This is what is the law of conservation of linear momentum says. Law of conservation of linear momentum says that the linear momentum of the system after the event has taken place will be the same as before the moment which has taken place, that was equal to 0. So it's a very simple system, and this very simple system what we find is that m1v plus m2v is equal to 0, or I can simply calculate, it's very easy to calculate this, that the velocity is equal to minus times m2, the mass of the gun, upon the mass of the, the mass of the bullet divided by the mass of this multiplied by v. So after this we have whatever we have done numerically, and if I have just shown you over here that this is the velocity v and this is the velocity v with which the gun recoils. So heavier the gun, it will have more mass associated with it, but still it all depends upon, nothing depends upon whether what is heavy and what is not. It all depends upon the nozzle velocity, the mass of the bullet upon the mass of the gun. And this negative sign, it shows that if the velocity v is in this direction, then this is actually a recoil velocity, which can be given by this relation, and it's a very simple situation. So next, so try to understand. The nuances are as follows. There is no external force, only internal forces are there. Sum of those internal forces is 0, and the momentum is whatever is constant. Could be 0, could be non-zero, could be positive, could be negative, but it will be conserved. Okay. So conservation of momentum, a very, very important item. One thing I would like to share with you before I go to the second example, and that is the example of a rocket. Propulsion of a rocket. A rocket is a total entity which has got some internal fuel. The internal fuel is made to eject out of the rocket in this direction with certain internal things which happen, and it so happens that the rocket is provided with a speed, with an acceleration, and we'll see in the due course like this. But there is another event which may happen, and that is, suppose there is 2 billiard balls and they come and one ball comes and hits the other ball. There is a collision, and in this collision there may be multiple collisions also. So at all moments of time, once this has occurred, then this event can be described in terms of momenta in mechanics, momenta, and in terms of energies. Mechanical energies normally are given. So when we attempt this problem, when we work out this problem, then you see, friends, that we are advised to use the law of conservation of momentum, not the law of conservation of energy. Because momentum is a pure phenomenon. It can be linear, it can be angular. Linear can change into angular, angular can change into linear. Like what happens, you see Anil Kumble bowling his ball, also any kind of spinners, when their ball, so it may go left, it may go right, it may go away, and there the linear momentum is converted into angular momentum, or angular momentum is converted into linear momentum, etc., etc. But energy is a very romantic concept. Energy is a very romantic concept. In the next chapter, we'll talk about work done, energies, etc., etc., kinetic energy, potential energy, this energy, that energy. There are umpteen kind of energies. But what I'm trying to say is that the law of conservation of momentum, it helps us to explain out the things more vividly, and often we fail if we apply the law of conservation of energy without thinking. Because once we do the formula physics, I have spent quite some time in explaining to you a very simple phenomenon like the recoil of a gun. To our minds, particularly when we are young, these aspects do not come, and that is why I thought I would share with you so that you can develop a tendency to think and to apply. Okay, next. So next we are talking about rocket propulsion, in which the principle of conservation of linear momentum we discuss. And as you may think of, and it's not rocket science to understand what a rocket looks like. The rocket is a very easy device. This rocket carries its own supplies, and supplies of liquid oxygen and appropriate fuel like kerosene or whatever grade of fuel is there, and together they burn, and the stream of burnt gases exhausts here, or like I have shown over here, exhaust at a very high temperature and pressure, through the exhaust nozzle. And this exhaust takes place in the direction just opposite to the direction of propulsion of the rocket. Here I am giving a schematics. Such diagrams are called schematic diagrams, where the scheme of things are proposed. So the rocket at a time t, at any given time t, has a mass m initially at that time, and it is moving with the velocity capital V, and so that it experiences a resistance kind of thing, which is of course in the opposite direction, which this system has to overcome or provide for this resistance, and which I have shown to you here that at a time t is equal to t plus delta t. This time is t plus delta t. At this time, of course the delta t can be very small, as we will see. What happens is, now when the system is operating, then a mass, a small m, is ejected per second. So this doesn't have, this is kilograms per second. As a result whereof, the mass of the system decreases. If delta t time has elapsed, then n into delta t is the matter, the gases that have exhausted from it, and of course the velocity of the rocket, it enhances to capital V plus delta V. And here I am just giving the schematics of what happens to the mass m delta t, which is ejected with the velocity v, small v, so that the net velocity of this mass as compared to the rocket I'm writing WRT with respect to. WRT stands for, and everybody knows that, WRT with respect to the rocket. So what will happen is that this velocity, whatever is happening to this, will happen relative to the velocity of the rocket, and the rocket velocity is v plus delta v. So because it is in the opposite direction, then therefore it gives v plus delta v minus v. And now at time t, we start with this. At time t, it could be any time. This time t, as I said, time t is equal to 0, etc. is very interesting. It has to be borne in mind what time we are talking about. So we have to be very clear about time t, t0, time t is equal to 0, 0 plus 0 minus, etc., etc. Okay, so this is our starting equation. All we have to do is, this is for this event at this moment of time. Later on these events are taking place. For this we write the equation for the momentum and then apply the law of conservation of momentum. So at t is equal to t, we found that the mass of the rocket is capital M and the velocity is capital V. So better write it like small p. Okay, so p is equal to mp. At time t is equal to t plus delta t. Here, what we have, that the total momentum of the system is enhanced, which may result in velocity, it may result in acceleration. We will have to see and check. So this I am writing as the mass of this body becomes equal to m minus m delta t. Okay, this is the mass, and the velocity becomes v plus delta v, change in the value of the velocity which has been depicted over here. And of course for this, m delta t into v plus delta v minus v. This is how the fuel, it is exhausted. So this is the system that we have, and now I multiply this with this. So with v, vm, any mv, m delta t into v here, then I have m into delta v, and when I multiply it with this, I get m delta t into delta v. Then the second term, I write it here, m delta t into capital V, m delta t into capital V just over here, m delta t into capital V just over here, and minus mv into delta t over here. So these two set of terms I have just shown to you. Sum of the two will become equal to 0, and what we are left with is that mv plus m delta v minus mv delta t is equal to 0. So proceeding from there, I just take off this when I come back. So these terms, they cancel out, and we get delta p is equal to m delta v minus mv delta v. Now the rocket faces resistance R, as I showed to you, during its motion, which means that my delta p is equal to, because it is in the opposite direction, the R, the reaction, the resistance, so delta p is equal to minus R into delta t. Okay, it's like impulse, I will be telling you shortly. And so I can write that delta p is equal to minus R delta t, substitute in this relation, and I will get minus R delta t is equal to m delta v minus mv delta t, which if I divide throughout by delta t then I'll get this delta t cancelled, minus r will become equal to m delta v upon delta t minus mv, because delta t will cancel with delta t, and I get this relation. And in the limit that delta t is very small, delta t goes to 0, this gives this one r from this relation minus r m delta v upon delta t, which I can write ddt of v in rate of change of velocity, which is of course the acceleration, minus mv as it is we put here. Okay, so rearranging terms, I get m delta v, I'll get, wait a second, I'll get m delta v ddt of v is equal to mv minus r. So dv dt I can write here as mv minus r divided by capital M, and capital M now I describe as the initial mass mi minus mt, where this is the mt is the mass. Again this mv, because m is the mass per unit time, so this becomes velocity into mass divided by time, it is mass into acceleration, and r is itself a force, the resistive force. Then I will get the expression here dv dt as in this particular form, where dv dt is the acceleration, this part, here it is the force total, and this is the mass in kilograms. So I get the rate of change or acceleration is calculated like this. So it may happen that r may turn out to be equal to 0, and in that case this dv dt becomes equal to mv upon mi delta t. So I can write it here, can make use of this space, and I can write this as, if r goes to 0, the acceleration dv dt, if r becomes very small, like in the outer space, there is nothing to do that, r tends to 0. So what I can write here is that dv dt, which is the acceleration of the rocket, this is equal to mv, because there is no r then, mv, and remember this mv is not this mv here is not linear momentum, this is the force, this divided by mi, the initial mass, minus mt, which is also a mass, because this is the mass per unit time and this is t is the time. So I get the expression like this, and you can see that for acceleration to be large, what is acceleration? This is the acceleration. Acceleration to be large, what should be large? The velocity with which the gases are being ejected out, okay, should be higher. So the acceleration is kind of described by the mass per unit length which is ejected, the velocity of the ejected mass or the fuel, initial value of the rocket, and the time for which the motion has taken place. So the next item that I am going to talk to you about is the definition of, just a small definition of what is known as impulse. Impulse. It's a very interesting phenomenon. Impulse takes place. This impulse is a function of, I'll do away with this part. Okay, the black ink is not proper. So although for the description of the physical associates of the laws of motion, whatever we have studied is sufficient, but historically there is another term that we need to learn, okay, and that actually impulse is a function of the magnitude of the force plus the duration for which the force has been applied. Okay, force exists or force fades away. Like when we have a hammer and we have to put in a nail in a wooden plank, then if we apply the force very slowly, then naturally the response will be different from if we hit it fast, then it will what is the requirement will be done. So it is the function of the magnitude of the force and the duration of the applied force, which I can say in terms of F multiplied by delta T. The unit of F is newtons and that of delta T is second, so the unit of the impulse is Newton second, and you can see that impulse is nothing. But if I define Newton second law, delta P upon delta T, the rate of change of momentum, multiplied by delta T, and the two of them cancel out. So what is left is delta P, which is nothing but mv minus mu. The momentum after and before. Okay, so it is basically what we can write is the change in the momentum of the system. Now, the before I take the next topic, and in between I'll give you some numerical examples, just discuss 5-6 questions and how we address those questions. But since I have just used the word question, then please, my dear friends, if you go back to my lecture number 1, and the whole purpose of doing this lecture series was UQVA. You query, you question, and we answer. But except for a few telephonic calls, your questions have not appeared or your criticism has not appeared. And I told you that whatever I know is 80% due to my students. So please be one of those students who make my life difficult, okay, who make this my old brains think again, polish me. And next topic, after we take those half an hour question answer series, there will be numerical questions. I am waiting for questions. Otherwise, you can ask the questions in my channel. I'll be able to see them and then try to answer them to the best of my knowledge. And thereafter we go for something beautiful, a lovely concept, which is the concept of friction. So friction we will take up, but even to start with, I'll tell you that friction is a manifest of the electromagnetic forces. It is the only fundamental force which manifests itself in the form of friction, which was studied much earlier than the discovery of electron or a proton or a neutron, which happened about a century back. But the friction has existed all the time friction is responsible for, even if I walk on this floor, then friction is responsible. Our cars move because of the friction, etc. We'll talk about that, but in between we'll have one lecture where I deal in some numerical problems and tell you how the various nuances of the laws of motion, the conservation of linear momentum, etc. Just to part with, I will tell you, like conservation of linear momentum, there is another conservation law, and that is the conservation of angular momentum. We'll deal that when we talk about those